I don't remember.
Yeah, I think it's pretty interesting. From what you were saying, it's like a pretty hard overall.
The central charge.
Yeah, it's only sure. Well, you can.
You're hiding in the back. Shall we start? Who's chairing?
Yeah, who's chairing? I don't know to share all the stuff.
Well, I can just start. You don't have to.
I have a last.
Right?
Can you share?
Shall we start? Okay, so I guess let's start again. So were there any questions about the last lecture, maybe before I start and continue? One thing maybe I should say, because I didn't say the word, what I gave, the derivation of the soft theorems is called current algebra. So this was a current algebra derivation of the soft theorems, because one person was asking me. Any other questions? If not, I guess let's continue where we ended. So where I ended was with this action in the new coordinates of our theory. And this thing you should really think of as oops, there's a square. You should really think of as a power series expansions in these. So you just expand it out and get an infinite number of these terms. So at this point, I mean, there's a number of obvious exercises that I could have asked you to do. So one is, I guess, to work out what the transformation properties of these pi's are under an infinitesimal SON rotation. SON minus 1, the unbroken one is obvious. It just rotates like a vector, but you might want to work out the broken, the translations under the transformations under the broken generators. And you might also use it to show that the action is invariant. Either you can do it by brute force, or you can show that the object d mu pi, by which I mean this thing, under an SON rotation transforms by a field-dependent SON minus 1 rotation. So this is something else you can show, and then it's clear that this action is invariant. The next thing you could do is you could derive the current that you get as a consequence of the invariance, and you can show that it's of the general form we had. So there's the d mu pi piece, or v d mu pi. And then there's the nonlinear terms that give rise to the non-trivial commutation relations. And yeah, so I don't know, are there any questions about the, just to see again, no questions? Okay, so then the goal for today, or let me still write it here, or the goal for now. So remember that sigma is massive, the pi's are massless. So according to our general arguments, what we should be able to do is derive an effective action that only involves the pi fields and that reproduces the S matrix for pi-pi scattering in the full theory to any desired precision. So how accurately you want to reproduce it is something I guess the experimentalist or you yourself have to tell you. Maybe you want an approximation to 1% or something, and then you have to figure out what effective action you should use. In this, we'll try to see how to do this in a systematic way. And there's various ways we could do this. In this case, the theory, our UV theory, is so simple that we could have just done the sigma, the functional integral over sigma. This gives us something that's naively non-local because you have the 1 over box minus m squared, but you can expand them out order by order. So you keep the terms that you want to the desired order. The other thing we could do is we could match the one particle irreducible actions in the two theories. You could also match directly the scattering amplitudes. Or really any other type of observables you like. For example, if you're in a time-dependent background, you might want to match in correlators. Now, morally, these all give you the same thing. At a technical level, they're slightly different, and you can see it in a very simple way. So if you match the 1pi effective action, for example, you get a very specific set of coordinates on your field space. On the other hand, when you match the scattering amplitudes, these are invariant under field redefinition, so you might use a different set of coordinates in the UV and IR. But more, I mean, at the end of the day, the physical on-shell observables here will all be the same. And I'll use this one on the one hand because I like scattering amplitudes. On the other hand, because this is something you can also do, for example, when your UV theory is not a field theory. So you could even do this kind of matching. If your UV theory is a string theory, you compute the scattering amplitudes or the S matrix in the string theory, and you write down a field theory, compute the scattering amplitudes, and match them. And this is one way you can think of the low energy effective field theories or the low energy effective actions, the type 2b, type 2a, type 1 supergravity actions as derived from string theory. You might compute the scattering amplitudes in string theory and write down a field theory action that reproduces them. So in this you can do also when you cannot do these kind of things, for example. Okay, so what we have to do now in this step, we have to understand to what order. So let's So this I'll match the scattering amplitudes, and the question we should ask is what diagrams contribute at a given order. And the answer to this we already saw in the first lecture, so this is given by the power counting, so we should understand the power counting for this theory. And so the let me denote, again, we imagined computing some diagrams, and it will have some external lines, some external pion lines. And then this is the number of external pion lines. Then E sigma, I'll call the number of external sigma lines. And obviously, in my low energy effective field theory, I only have pi, so this I will actually set to 0. Then I have internal pi lines. Then internal sigma lines. And then I have a bunch of vertices. So I have a cubic vertex for sigma. Let me call it this way. And then V, the quartic vertex, let me call it this, and this is probably too small. Okay, so this is V subscript 3 superscript sigma, and then I have the other interactions that involve the pi's. So I have V, an nth order vertex, so n pion fields. Then I have an interaction that's linear in sigma, and has the pions in it. Again, this has n pion fields in it. There's different types of them because I'm expanding out this action. And then I have one contribution where I have sigma squared and n pion fields. So these are all the number of different types of vertices. And now what we should do is write out the scattering amplitude, or the contribution, the scaling of the scattering amplitude for a given diagram. So for each of the, and forgot the number of loops. So for each loop, again, we get integral d4p over 2 pi to the 4th, which I'll just write as p squared over 4 pi to the 2l for each of the loops. And then for each of the pi propagators, they're massless, so we get 1 over p squared raised to the number of the internal pion lines. Then there's a number of contributions really from an internal sigma line, because we can expand the propagators out, and it gives a 1 over m squared plus p squared over m to the 4th, and so on. So what I'm writing now is going to be the leading contribution to a given diagram, in which case it just contributes 1 over m squared raised to the power of the number of internal sigma lines. And now we have to figure out how the vertices contribute, and the action was here. So the lambda v, let me write it in the following way. So let me write lambda. I can always also write, remember, m squared was lambda v squared. So lambda I can always write as m squared over v squared. So I get for each, so the cubic vertex contributes m squared over v squared times v. Then we have m squared over v squared then for the quartic guy cubed. And then for the quartic guy we just have lambda, which I'm writing as m squared over v squared. And then we have all these other guys, and they contribute 2 derivatives for each of them. So we get a p squared, and then we're summing over all the n's, and we get vn, let's just pi, plus vn sigma pi, plus vn sigma squared pi, and then we get the powers of 1 over v squared. We just get 1 over v squared, and then by dimensional analysis we just get n minus 2 over 2 for each of the ones that just have the pions, plus n minus 1 over 2 for each one with the sigmas, one more here because we have an additional suppression for each sigma because it enters as sigma over v, plus n over 2 vn sigma squared pi. And these are not all independent. So again, like in the previous power counting, we have conditions that all the external pion lines have to end on a vertex. So all the pion lines, not just the external ones. So we have e pi plus 2 times the number of internal pion lines. It just has to be, so here by definition we have n, so we just have n times v n pi plus n times vn sigma pi plus n times vn sigma squared pi. And then similarly for the sigmas, and this I'll set to 0, plus 2i sigma. And then here we have the cubic guy, so we get 3v 3 sigma plus 4 v4 sigma plus sum over n vn sigma pi plus 2 vn sigma squared pi. And then the last one is again our topological identity. So we have the number of cubic vertices plus quartic vertices plus sum over n vn pi plus vn sigma pi plus vn sigma squared pi minus the number of internal lines plus the number of loops is equal to 1. And then the way you usually do it, just solve here for the number of internal lines and plug it back into the thing, and we find that the scattering amplitudes have some overall p squared, then a 1 over v squared to the raised to the power of the external pion lines over 2 minus 1. Then there is a p squared over 4 pi v squared to the power L. And then we have p squared over m squared. And then this is 1/2 v3 sigma plus v4 sigma plus n 1/2 n sigma pi plus v n sigma squared pi. So this is what the amplitude scale like. And then notice that in this case, we have a double expansion, slightly different from the one I wrote last time. So we have an expansion here in p squared over v squared, and one in p squared over m squared. And so if we want to calculate to a given order, you might want to think about it as an expansion. So we have d, if I call this here d, and this one L, and then the leading order is just at the origin, no loops, and d set to 0, and then the next order might be d equals 1, so suppressed by 1 power of p over m squared, or we could have one loop, and so on. And this term in the weakly coupled regime, this mass is smaller than v squared, and so this is larger than this one, and so on. So we have some expansion that's organized in this way. Now, one question you might ask is, why is it a double expansion? Is it clear why it's a double expansion in this case, what the two expansions are that are going on from the point of view of the underlying theory? This goes back in a way to the question by Oliver, who isn't here. But so the reason is that the coupling in this case is not necessarily, or I'm not assuming that the coupling is order 1. I'm allowing for a small coupling, and this is what appears here. So naively, we have an expansion, a derivative expansion, and then the expansion in the coupling. If the coupling is order 1, this is just v squared, and we're back to the formula I had. But here I don't want to assume it because we want to do the matching in the weakly coupled theory, but you just can keep track of it. I mean, you don't have to assume that these things are order 1. Okay, does this make sense? Okay, and so then let's assume for a second that we're at low enough energies so that the leading term is actually enough for what we're interested in. The leading term is just d equals 0 and L equals 0. Has d equals 0 and L equals 0. Now L equals 0 is clear what this means. It means we're doing tree-level diagrams. D equals 0. These are all positive numbers, so this is greater than or equal to 0. And notice that all the vertices that involve sigma actually enter there. So we have the cubic guy appearing, the quartic guy, and the other ones. And so what it means if we set it to 0 is just that we don't have any vertices that involve the heavy sigma field. So this is tree level and no sigma vertices. And so this makes it obvious what the effective action is at this order. It's just this action with all the sigma stuff dropped. Let me call it 0 maybe. And let me call this, like I introduced it before, let me call this d mu pi. D mu pi. Does this make sense? And so here what we say in this case is that as we take the mass of this field to infinity, it has no effect on the low energy theory, so this means that the sigma decouples. And this really should always happen. So if you take the mass of the heavy guy to infinity, it shouldn't affect the low energy physics. Now, let's use this action and just look at the scattering amplitude. So we didn't even have to do any matching of the scattering amplitudes, but let's compute the scattering amplitude and show that it at least reproduces the properties that we said it should have in the last lecture. And so let me write it out. So we have the vertex. Let me just go to the first, so the leading order, and look at 2 to 2 scattering, d mu pi, and then from the the two 2's in a way here cancel, and we get 1 over 4v squared p squared d mu pi d mu pi. Now, if we calculate the scattering amplitude in our theory, let's say we're computing the process P1 with, let's call this a flavor I, P2 with flavor J, goes to P3 with flavor K, P4 with flavor L. Then we know from our word identities for the unbroken group that this has to be built from invariant tensors of the SON-1 group. And the only things you can write are, so there can be some general function multiplying delta ij delta KL. Then there can be some other function multiplying delta ik delta JL. And then let me write it here. And then another function multiplying delta IL delta JK. And you also know that these things are related by crossing. In particular, we have the T of S, T, and U, we just obtained by sending P2 to minus P3 and vice versa, which means we're exchanging S and T. So we have this is A of T, S and U, and the other guy, R of S, T, and U, we get by exchanging S and U. So if we want to compute the scattering amplitude, we really have to only compute one of these guys. I'll call this one annihilation, because it gives rise to processes where you have two guys with the same flavor and you get out two guys with a different flavor. So the way we can compute A, or let's look at what an amplitude looks like if we have P1I, P2I goes to P3K, P4K with I and K different, then you see that the only thing, this one then becomes 1 because I is equal to J, K is equal to L, and all the other ones don't contribute because I is, anyway, these don't contribute. So this is just A of S, T, and U. So this is the only process we actually have to compute. And what I'll do, let me draw this this guy diagrammatically. So I'm drawing solid lines for the flavor indices, and then I'll draw some dotted lines with a dot, something like this, for the derivatives, for the side where the derivatives are contracted. And you see that they're always contracted in the same way as the flavors. So in particular, there's nothing here. So then, what are the diagrams that we have to compute in this theory? So we get A, STU for our process here. This is just, well, let me put the I in. Then we just get an I from the vertex that we can read off. Then the 4 actually cancels because we have two ways of contracting these guys. Two ways of contracting these guys, so we just get 1 over v to the 4th. And then we have two contributions, really. Well, let me actually draw the diagram so it's clear what I'm doing. So there's this diagram, and there's this diagram. And so then again, this one from the vertex, I get an I. Then I said I get a 1 over v to the fourth, and then I just get the momenta p1 dotted into p2, and because it's acting on two particles in the in state, I get a minus sign because it's acting on e to the minus ip on both of them, which cancels the minus sign in my vertex, so I just get p1 dot p2 plus I over v to the fourth p3 dot p4, and then you recognize this is just s over 2 for massless particles. This is s over 2, so I just get I s, v squared, sorry. Did I also write it wrong there? No. So this is just I s over v squared, so that our full scattering amplitude at this order is just s over v squared delta ij delta kl plus t over v squared delta ik delta jl plus u over v squared delta il delta jk. So this is the scattering amplitude for 2 to 2 scattering that you get for our pions. And then what we said is that it should be soft as we take the momenta to 0, and you see this actually is the case. So if this involves the momenta. So if we take p1 to 0, it goes to 0. If we take p2 to 0, it goes to 0. And then this one is obviously the same as this one by momentum conservation. So if we take p3 or p4 to 0, it also goes to 0. And what you can do, if you want, is use this theory to verify. So as an exercise, you can verify our soft pion theorems for the process where you have, let's say, P3 with flavor K, P4 with flavor L, Q1 with flavor K, Q2 with flavor L, and then P1 with flavor I, P2 with flavor I, and these can all be different. So yes, you can take I not equal J not equal K, and you probably you can do it just by brute force, obviously, but you can also look at which diagrams actually have a chance of contributing in the limit where you take Q1 and Q2 to 0. Okay, so this is the leading order. Are there any questions about the leading order? There are? Okay, so then let's go and compute the first interesting piece where we actually do a matching. And let me see, there's probably some stuff I want to keep. Maybe it's good to keep. Yeah, this could be useful. Oh, sorry, there should be dot, dot, dot.
Okay, that should be the only thing.
Yeah. This is the only thing that contributes at the 2 to 2 scattering. But for example, if you want to compute, do this, then there's also the sextic, and then at higher orders the octic. Yeah, so they're all there. Okay, so now what we might want to do is, let's say that we have a slightly larger momenta, and to get 1% accuracy, we actually need to keep the leading correction. The leading correction is just, in the weakly coupled theory at least, is just the p squared over m squared correction. So let's consider d equals 1. And then our effective action, obviously, we should write down the most general thing we can write down is what we said that's compatible with the symmetries. The fact that it's p squared means we have 2 more derivatives than we had before. And so this is our new effective action. Oops, pi. Plus, and then some coefficient divided by v to the 4th of d mu pi squared. We can certainly have this term just because this one was invariant, so we can write this one. The other one we can write is d mu pi. So these guys go together, and then d mu pi. And this is really all we can write at this order. And so what we should do is we should ask, how do these things contribute to the scattering amplitudes? And at leading order, so you can match this in any process you like, really. But you should always look for the simplest process, and this contributes to 2 to 2 scattering. So we should look at the 2 to 2 scattering process. And for 2 to 2 scattering, again, you already have 4 pi's if you have just the regular derivative here. So you can, for that purpose, replace all these covariant derivatives here by regular derivatives. And then again, also in this case, I mean, this argument only relied on SON minus 1 invariance, so we can use it here. And again, we just have to compute the process that we computed over there, where we have the ingoing guys both with one type of flavor and the outgoing guys with a different type of flavor. Now, what is this vertex? So this vertex, in the way I've been drawing it, well, just looked like this. So we have flavors contracted in the same way as the derivatives. Oops, sorry. Yeah, no, it's correct. And then over here, we have it contracted in different ways. You have a question? Or no? Okay. And the dotted lines are supposed to be the derivatives. You can draw them in other ways if you want. I don't know. Or you can just put a dot here. I don't know. I'm just saying this momentum will be contracted with this momentum in this vertex. This momentum will be contracted with this one, and here it goes this way. Yes. Okay, and so then the amplitude we get, we can really just read it off. So there's an amplitude we get at this order. So let's call it 1. So the contribution from these things, well, let's put the I back in. So we get an I from each of the vertices. Then we get the C1 over V to the 4th, obviously. Then when you look at it, the first guy can attach to 4 lines. The second one here has 2 choices. So this is 1, 2, 3, 4, let's say. And then in this case, we really have, let me draw the diagrams out so it makes sense. And then so we have I, K, K, plus, then I have a diagram where I have well, let me put the numbers here of the guys. And so we can just read it off. So we have I times our annihilation amplitude. So in this diagram, really the first guy has 4 choices, the other one has 2, so we get a factor of 8. I C1 times 8 over v to the 4th. And then here we don't get a sign because we have a minus sign on both sides, so we get a plus sign, and we get p1 dot p2, p3 dot p4 plus, and then from this one here we only get a factor of 4 because we have this guy and this guy, so we get I c2 over v to the 4th, and then we have p1 dot p3 and p2 dot p4 plus I c2 over v to the 4th, and then here we just have p1 dot p4 and p2 dot p3, and again you recognize this one as s squared over 4, this one as t squared over 4, and oops, and I forgot the factors of 4. So this is t squared over 4, this is u squared over 4. So what we get at the end of the day is a contribution that looks like this. So A is 2c1 over v squared s squared plus c2 over v to the 4th t squared plus u squared. Okay, so this is the contribution, the contribution we might get at tree level from our new effective action, and now we should compute it in the UV theory and adjust these coefficients so we reproduce the amplitude. That's the one I wanted to keep. Okay, so in the UV theory, I just erased my contribution, but I think D was 1/2 3 sigma plus V4 sigma plus N sigma pi plus Vn sigma squared pi. So what we want to do is have a diagram with 4 external pions that has d equals 1. And the only thing we can do, as you see, is have 2 of these kind of vertices, which means the only diagram we really have in our theory is this guy, where, okay, now my notation is getting a bit horrible. So this one is a sigma line, and these ones are the pion lines, and we have the momenta contracted here. So this is really the only contribution that we get at this order. Does that make sense? And so I also may have erased the action by now, but the coefficient of that term, so the interaction piece that we're interested in, was just, so we had the 1/2, 1 plus sigma over v squared, so the 2's cancel, so we just get sigma over v d mu pi And so what we want to compute is this contribution again to the same process, so the same configuration with same flavors for the ingoing particles and same but different from the ingoing guys for the outgoing particles. And so what we get then is I times the first order contribution of the amplitude in the UV, let's say. This just, we get a I, so we get minus I from the vertices. Then we have 2 of these guys, so this is again 1, 2, 3, 4. So we get P1 dot P2, P3 dot P4, and then we have our propagator, which is just S minus m squared plus I epsilon if you want. So this is, and then we have a 1 over v from this guy, 1 over v from this guy. So we have a 1 over v squared. And then we also had 2 options here, 2 options here, so we actually have a factor of 4. And this guy, again, is s over 2. This is s over 2, so we get an s squared over 4. So we get minus I 1 over v squared, s squared divided by s minus m squared. And to the leading order, what we're interested in is the limit where s is much smaller than m squared. So this is minus I, well, plus I actually now, because I get this out, s squared over v squared m squared. Okay, so that's the amplitude in the UV theory. And for the 2 amplitudes to be the same, at this order, just tells us that we're not generating the C2 piece, but we're generating a C1. And so we have a 1. So this is v squared over 2m squared, the way I've defined the C1. If I then divide by the v to the 4th, I get this amplitude. And so the action at this order is 1 over 2 v squared m squared d mu pi squared. And this reproduces all processes at this order in p squared over m squared. So you can also now use it to compute 3-to-3 scattering or any other process. By symmetries, you know they have to be related. So this is the action that you can use for any computation at this order. One question you might ask, I said something about it earlier as to why these things are supposed to be local. In this picture, you kind of get a more intuitive understanding why this might turn out to be local. If you look at the process that contributes in terms of time, so not the Feynman diagrams, but in terms of time, you might imagine that you have 2 contributions. So one looks like you have your these ones I had solid lines. So you have a process where you first create 3 guys from the vacuum, and then one of them combines with these ones, or you have a process. In these diagrams, all the lines are on shell, so I'm including the theta function, so you don't have time translation invariance. And so the point is that you're violating energy conservation. But this is okay in quantum mechanics as long as it only happens over a time delta t of order 1 over the energy scale that's involved, which in this case is just the mass of this particle. So this is the amount by which we violate energy in here in this virtual process. And this is a very high frequency for our low frequency modes. And they really should see this as basically instantaneous. We just don't have any modes that resolve this kind of process in the low energy theory. And this means it will be local in time. And then because this thing can only propagate at most at the speed of light, it will also propagate only a distance much smaller than the wavelengths that you can resolve in your low energy theory. So in that sense, it will be is one explanation for why these terms come out local. Okay, so this was nice. I mean, we can do the matching order by order. We can surely go to higher order, just include more terms, can compute more diagrams, make sure that our amplitudes agree. But the effective field theory, in a sense, is actually more powerful than this, because you can also use it when you cannot compute the UV theory because lambda is order 1, let's say, and your expansion breaks down, because it really implements, no matter how strong the coupling is, it won't break the symmetries. So you can still use this effective action as long as you're interested in terms of order p to the 4th in this case. Yeah?
Could you repeat why you just have derivative terms in the effective action?
Sorry?
Could you repeat why you just have derivative terms in the effective action?
As opposed to mass terms? Or?
Yes, for instance. Or, for example,
the mass terms just wouldn't be invariant under the symmetry. So you don't just have to write down terms that are invariant under the unbroken symmetries, but you have to write down terms that are invariant under the full symmetry group. And anything that you construct just out of pi's, because the leading transformation of pi is just a shift in pi. I mean, if you imagine the coordinates on the sphere and you do one of the broken guys, you're just shifting the pi by a constant. So anything that you add that doesn't have derivatives acting on the pi's in one place or another in the vertex just violates the symmetry, so you can't really add those. Yeah.
If you would match the one loop, I guess you would have a divergence regularized.
I'll talk about that in a second. So, but yeah. So I'll just right now I'm just arguing that you can actually compute loops here, and then I can sketch how you do the one loop matching. The one loop matching, yeah, it's interesting. I can't do it in detail just for time reasons, but I'm actually happy to explain it in detail to anyone who's interested. I don't know. One thing that's interesting, for example, about the one-loop matching is you might ask how you regularize or regulate how you work with the theory that we've written down in terms of the sigma and the pi, because it looks like a mess. And really, you probably shouldn't work with that to work out what the counter terms are, because you know that all that stuff is UV physics, which shouldn't know about the state you put the theory in. And so you can work out the counter terms you have from the unbroken phase, which is very simple because it's just your d mu phi squared minus 1/2 m squared phi squared minus lambda over 8 phi to the 4. So you can work out the counter terms there. You know you only have 3 counter terms, the wave function normalization for the phi's, the counter term for the mass, and then for the coupling. And in fact, at one loop, you know that you don't even generate a wave function renormalization. So you only have the mass counter term and the counter term for the coupling. And those have to actually be enough. And so, yeah, we can see it in a bit more detail maybe. Okay, yeah, so the next point I wanted to make is just that you can still use this theory even if lambda is order 1, because these are all the terms that you can write down at this order. And so, so the one question you can ask is the one you just asked, is what about loops in this theory? What about loops? How does renormalization work? And it should be clear in a way that because we're writing the most general thing at that order, also the divergences must somehow be proportional to these things, and we must be able to absorb them. So we can do the calculation explicitly. I can't do it in real time, unfortunately, but I can draw you the diagrams you have to compute. So they're all coming, the leading diagrams are all coming from this guy or from the vertex we used before, the -1/4 v squared pi squared d pi squared. So we can, and again, the only thing you have to compute is this annihilation piece of the amplitude. So let me just one loop. This is in the IR theory now. Is equal to, and there's a number of diagrams because you have a bunch of vertices. So there's, what's interesting is that there's a bunch of diagrams. So first of all, you have this diagram. These have a symmetry factor, so there's a 1/2 plus 1/2, where you have this guy on the other side, plus the various other pieces. So these are all order n, because you have a closed loop here. And then you have diagrams that look like this. Plus ... And then you have diagrams that look like this. And always all possible ways of sprinkling the derivatives around. And then you have diagrams that kind of look like this, again with all possible ways of sprinkling derivatives. So you see that there's a number of pieces that you have to compute. And I'll just give you the final answer for the amplitude. And so then what you find so this is 3n minus 7 is what I got over 96. Some of these numbers will be looking weird, but we'll see that they actually make sense the way they are. So this is s squared plus, and I'm using, so this is in dimensional regularization. Epsilon bar is the usual thing. It's the 1 over epsilon minus the Euler gamma plus log of 4 pi. Plus, and then these numbers look even stranger, but I'll argue in a second why they also make sense. So there's these kind of pieces plus 13 t squared plus u squared over 288 pi squared v to the fourth, and then there's a bunch of logs, which should be clear from this diagram because we get a cut when these guys go on shell. So we have, and there's pieces that go like n in the term that has the log in s. So there's n minus 2 s squared log of minus s over mu squared divided by 32 pi squared v to the fourth, and then we get the ones that are involving log of t and u. So we get 1 over 192 pi squared v to the fourth, and then s squared minus 3t squared minus u squared log of minus t over mu squared plus s squared minus t squared minus 3u squared log of minus u over mu squared. So this is what the amplitude looks like that you get. And one of the things that you know, or one thing that should happen, for example, when you take n equals 1, this should all go away, because for one guy, you know the metric, you can always just change coordinates so it's flat and there's no interactions on these guys. And when you set n equals 1, for example, you get 9 minus 22, so you get minus 13, which is the same 13 as here, except here you have it with a factor of 2. But this appears also, so this all is multiplying delta ij, delta kl, and this cancels for the one flavor case pieces in the t in the delta I k delta jl and delta I l delta jk pieces. So this is these two have to be the same at least, and the same is true for the other pieces. So this is the final amplitude, and now you see that the divergences we get are exactly of the same form as our tree-level scattering amplitudes over here from these new vertices. So really what we should do at this order, we should add these contributions, and at the end of the day, really what will happen is you get rid of these, you get rid of this, and then this one right now, it depends on the scheme you're choosing. So these are all scheme-dependent things, and we can just define some renormalized couplings, which will depend on mu now, to make sure that the physical amplitude doesn't depend on mu. S squared over v to the fourth plus c2, some renormalized coupling of mu t squared of u squared over v to the fourth. And so you see that the pieces in your amplitude that are polynomial, they correspond to local terms in the action, and they're not really calculable, but the pieces, the logs are actually calculable. So the coefficients here are fixed, and they're not affected by any higher order operators that you add. So you're actually making some predictions. And then if you want, all you have to do is measure these two things, and then you can use your theory. So that's the one loop thing. Does that make sense? And then one point I can make, just because you were asking me about the divergent structure. So as I said, the only counter terms you had in the other case really are the renormalization of the vertex and the renormalization of the mass, or the counter term for the mass of the sigma guy. And you see that this only really contributes to s squared. And so something interesting still has to happen for these guys. And this just means that in the IR theory, you have to include additional diagrams. So if you do the matching at one loop, what you have to include in the IR theory. So there's these kind of diagrams that we just computed. They're also there in the IR theory. But then there's things that look like this. And plus there's stuff that looks like this. And then there's the counter term. This guy. And this has to equal the thing we just computed, where this is the C1 counter term at one loop plus the C2 at one loop. So the structure would look like this. And then all the IR, all the logs are the same in the two theories, like here and here they cancel. But you screwed up the UV because this one also is singular as you go to the UV. And you see that this one actually contributes to exactly cancel the epsilons of the t squared plus u squared pieces. So you have to just add them all in. But you see that they don't contribute a finite piece. The way to see that they don't contribute a finite piece is that you can get the log by using unitarity. So the log you can obtain from the diagram where you cut these lines. And when you cut these lines and put them all on shell, the momentum in this propagator is much lower than the mass. And so then the finite pieces will go like 1 over m squared here, 1 over m to the fourth here. And so this really just goes to fix all the counter terms properly. So this is the matching you would do at one loop. Okay. And then, you can keep going. But you will always have, if you add enough terms, if you want to go to p to the 4, you just have to add all terms to order p to the 4. But then these will be the only ones that you can generate by your diagrams as long as your regulator respects the symmetry. So if you pick a bad regulator, you might generate additional pieces, and it just means you want to add non-covariant counter terms to your action or just use a better regulator. I mean, it's up to you. But okay, does this all make sense? So this was all I think I wanted to say about the matching in the linear nonlinear sigma model. Yeah?
The current algebra techniques yesterday have an analog of these C1 and C2 coefficients.
The current algebra really, in a way, just reproduces for you the tree level contributions, actually. So you would have to look at some subleading pieces that I didn't look at. So there's no, at least in what I did, there wasn't any. Okay, so what we did now, I guess, in this exercise with the linear sigma model, is we started with a theory that had an SON symmetry, and then we chose a potential, so the field got a VF and spontaneously broke it to SON minus 1, and then we integrated it out, and we got a theory that non-linearly realized SON with an unbroken SON minus 1. But this is we should be able to do this more directly. So we should be able to directly write down the action with that given set of symmetries that non-linearly realize some part of the group and linearly realize some other part. And the construction, or one of the constructions that you can use, so I think it's the standard construction that people use, is usually always referred to in the abbreviation as CCWZ. And this is Kalin, Coleman, West, and Zomino. So let me briefly sketch what the idea is. Yeah? Yes? Uh-huh. Which argument, sorry? This one? This one? So here I was just trying to give you a heuristic argument as to why you should expect to be the terms that appear to be local, why the effective action for the pi's should be local. And what I said is we can write out our propagator in terms of the piece that has the theta of x naught and the piece that has theta of minus x naught or x naught minus y naught, etc. Does that make sense? So here, this is supposed to be time. And then in that case, all the particles are on shell. And then what's the way to read it diagrammatically then is that you have one contribution where you just have the two pions coming in. They produce an on-shell guy, and then that guy decays. Or you have these guys from the vacuum. You produce three of them, two pions, one of these, and these guys combine with this one and disappear into the vacuum. And these processes violate energy conservation, and they violate it by an amount delta E. So the time scale over which it occurs is 1 over the mass of this heavy guy. In our low energy effective field theory, naively, we're only resolving scales frequencies much below the mass of these particles, and also length scales only much below the mass of this particle. So we've coarse-grained the system in a way. And this means that this basically looks instantaneous to these long wavelength modes. And that means it's local in time. And because this thing can only propagate at the speed of light, it only travels a finite distance, and it should be local in space. So that was just a heuristic argument as to why this might make sense, that you actually always get these local terms. Okay, so here what we have now is we might have some general symmetry group G, and you can always keep in mind our example. So it won't be totally different. In fact, it's essentially following the steps we did, but in a more general way for a general symmetry group. So we have a general symmetry group that acts on our field space. The field space here doesn't have to be a vector space. It can be a general manifold. And then we call, so the group or the subgroup that leaves what I'll call origin in quotation marks. We'll call H. So this is the kind of thing we had. The reason I put it in quotation marks because there's no natural origin on a manifold. But you can have a point, and you can just ask what the stabilizer of that point is. It's the origin in the coordinates that we've chosen, if you wish. So this is the origin in a particular set of coordinates that we've chosen. And what we will do we can parameterize our Lie group G near the identity at least, as so the general element we can write as e to the minus I pi and x. These were my broken generators. I'll just put vectors over everything so people don't complain about my small subscripts or indices, but this is just always running over I, if you wish. And then we have the broken generators where A. So I have another U. So they don't have the same dimension. These are the broken and unbroken generators. And this way of writing it makes it clear that G has a structure. So we have some group G. And then this guy is our parameterized, is our coset, G mod H. And then over every point in the coset, we have a fiber that's the group looks like the group H. So we'll parameterize our element this way. Okay, so next, let's imagine we have some set of, so this is just a crux that we'll use to get at the final answer, but let's imagine that we have some, our field theory, like our phi's, and we introduce some set of coordinates on which h acts linearly, so we'll call them the same we called them there. So I called them chi and xi, so these are the coordinates on my field space. They're both supposed to transform linearly under h, which means if I act with an element from the group H, what I should get is this transforms under some representation, chi, and this transforms under some other representation. And the x's are the ones that don't transform linearly. So these ones transform linearly under G. So now what we want to do is we want to find coordinates that give us a natural action of the group G on these guys. So we want to somehow separate. This is what we were doing in that case. We want to find coordinates that make this, so this locally looks like, so just locally looks like G mod H cross H. And we want to find coordinates that make this kind of a local product structure manifest. So the way we do it is we start from these coordinates, and then we know from our example of the sphere, for example, we can always find a transformation that takes any point on the sphere to the North Pole. So what we're doing, we're acting with one of these, with the broken guys, by acting with the broken generators. So we can act with e to the I pi, so these can now depend on x. These are our fields. We can always find a transformation that brings us into, that takes us to this form. And then what we can do is we can introduce new coordinates on this space by psi, no, let me call this one pi, as e to the minus I pi of x, and then psi 0. So this is just the definition of what I mean by this new set of coordinates. Does this make sense? If not, I mean, you should tell me. Okay, so this is our new set of coordinates. Now, one question you might have is, how does the group G act? So when we act with G on this guy, what we get is just from our definition here, e to the minus I pi x psi naught. And then this is an element in G, so we know how it acts, and we can always bring